general complex exponential series. Let S equal to sigma plus j omega be a complex number. We define x of t as x of t equal to e power st equal to e power sigma plus j omega of t equal to e sigma t e power sigma t in of cos omega t plus j sin omega t. General complex exponential complex due to j exponential e power. So j for complex. Then signal x of t equation 1.35 is known as general complex exponential. This is this equation, general complex exponential signal, whose real part here e power del of t into cos omega t. This is the imaginary part. Real part. Okay, real part. J is j sin omega of t. J sin omega of t is the imaginary part. J I sin omega t is the imaginary. This is the imaginary. This is the real part. Are exponentially increasing. Del is greater than 0. Condition del should be not say del sigma. Sigma is greater than 0 or decreasing. That is sigma is less than 0 in sinusoidal signals. Exponentially increasing means sigma is greater than 0. If exponentially decreasing means sigma is less than 0. Sinusoidal signals, figure 1.7, real exponential signals. Note that if s equal to sigma, a real number is the real number, then equation 1.35 reduces to real exponential signal x of t equal to e power sigma t. X of t equal to, this is a generalized signal. So x of t equal to e power sigma t. Here continuous time real exponential signals. Continuous time real exponential signals. A is sigma condition, sigma is greater than 0. Here in figure B, the condition is sigma is less than 0. That is here sigma exponentially increasing. Here exponentially increasing. Del sigma greater than 0 here condition. Okay. Here in figure B, exponentially decreasing. Exponentially decreasing. That is E is less than 0. Sigma is less than 0. Less than 0. That's why decreasing. Here increasing. Sigma is greater than 0. Here x-axis function of t, in y-axis x of t, x-axis time t, time t is you can say second here it is not required seconds are time. That's all. Here x of t equal to e power sigma t. X of t equal to e power sigma t. Here also same. But here condition sigma is greater than 0, then this way form. If sigma is less than 0, decreasing exponentially, here increasing exponentially. That's a real exponential signals. This is. So here condition is x of t equal to e power sigma t, t for this time, sigma, that condition is greater than 0 or less than 0. If greater than 0, increasing exponentially. If sigma is less than 0, then decreasing exponentially in this way. As illustrated in figure 1.8, if sigma is greater than 0, if sigma is greater than 0, then x of t is growing exponentially, and if sigma is less than 0, then x of t is decaying exponentially. Yeah, here decaying, here exponentially increasing, growing, exponentially growing. This is the exponentially growing, exponentially they are decaying exponentially here, like exponentially decaying. Exponentially decaying. Okay. The sinusoidal signals. Sinusoidal signals. A continuous time sinusoidal signal can be expressed as x of t equal to a cos of omega naught t plus theta. This considered as sinusoidal signals. In the sinusoidal signal can be expressed as x of t equal to a cos, that is here cos we already have seen, no? Cos e power alpha sigma t cos omega t for real part. So here this is for real part, another one imaginary part. Where a is the amplitude real, a is the amplitude. This is the amplitude. So this is the amplitude. So this is the amplitude. This is the amplitude. Okay. Omega naught is the radian frequency. Radian frequency. Radian frequency. Radian. Okay. Radian frequency. Omega naught. In radians per second. Unit is radians per second, and the theta is phase angle. This theta is phase angle. Omega naught is the radian frequency, and the theta is the sinusoid phase angle in radians. Unit is radians. The sinusoidal x of t is shown in figure 1.9, and it is periodic with fundamental period. Periodic with fundamental period. Periodic means t naught. Fundamental period means 2 pi divided by omega naught. The reciprocal of the fundamental period is called fundamental frequency, f naught. That is this reciprocal of fundamental period t naught here, yeah, this is the fundamental period. Fundamental period. This is the periodic. 2y divided by omega naught. T naught is the fundamental. So T naught is called the fundamental frequency. That is the reciprocal of the fundamental period. T naught is called fundamental frequency F naught. F naught fundamental period reciprocal here. Here is not reciprocal. So 1 F naught equal to 1 by T naught hertz units for frequency. From equation 1.38, 1.39, okay, this one and this one, we have W naught equal to 2 by F naught, 2 by F naught. From this equation, from this equation, from this equation 1.38 and 1.39, that is T naught equal to 2 by divided by the omega naught F naught, that is fundamental period T naught equal to 2 by divided by omega naught. Here fundamental frequency F naught equal to 1 divided fundamental period hertz unit. From here, from these two equations we can get a W naught. W naught equal to 2 pi F naught. These 2 pi coming here. So F naught is here. It means 1 by T naught. So which is called fundamental angular frequency. This is the omega naught is called fundamental angular frequency equal to fundamental angular frequency equal to 2 pi F naught, 2 pi 2 times of pi, 180 into 180. F naught fundamental frequency. Using Euler's formula, the sinusoidal signal equation 1.37, 1. Sinusoidal signal x of t equal to a cos of omega naught t plus theta. Sinusoidal signal in equation 1.37 can be expressed as a cos of omega naught t plus theta equal to a real of e power j of omega naught t plus theta. Okay, RE denotes the real part of. This is real part of. We also use the notation m. I am denote the imaginary part of here. So here sinusoidal signal can be expressed as, that is, a cos of omega naught t plus theta equal to a real part of e power j omega naught t plus theta. Im denotes, we also use the notation Im